So good morning. So welcome to this lecture of mine. It's on hardware description language. So it's HDL. So this is the first step of the digital design flow. So it is the step where you essentially depict whatever you have in your mind, whatever design is in your mind, and you would like to express that using a language. Okay. So this language that we will be talking about or we will be discussing on is actually the Verilog language. Okay. So Verilog is one of the languages. The other competitive language that we use is the VHDL language. Okay. So the question is that today in an 1.5 hour class, right, we will not have the time to discuss about all the syntactical features of Verilog, because it's a huge language. It has got a lot of features. Okay. So but rather what we will try to understand is that what is the principle of expressing a particular design using the language constructs of Verilog. Okay. So how is it different from other programming languages? Like for example, all of us know what is the language C to some extent at least, right? So we will try to rather differentiate what is the inherent difference between using the language Verilog and the language C, for example. Okay. So we will go step by step. So this is a brief history that we will be talking about. So this is actually how it started. Initially, when the Verilog language was started, right, it was not really formulated. That is, the syntax of Verilog was not properly postulated. Okay. So it originally started with gateway design automation. Then Cadence purchased it in 1989, and then there were some standardizations involved. But now we have a fairly good standard language, which is the Verilog language. Okay. So now what I mean by standard is that we have got an IEEE standard. So that means the worldwide people use the same syntactical features of Verilog. Okay. It's quite standardized. Okay. So essentially it was originally started as a modeling language. Even now it's a modeling language, and it is an event-driven logic simulator, which means that it works on the whenever it's triggered, whenever there are events. And rather later on in the history, it was pushed into more of a synthesis language. That is a language which is targeted for synthesis. Okay. So what is synthesis? You know what synthesis is? So synthesis is essentially the step of the digital design flow when you essentially push a design or map a design into the library. Okay. So library is the design library that you possess. Okay. So therefore the other competitive language which we use essentially is VHDL, and it is Verilog or VHDL, whatever. All these are examples of hardware description languages or HDL, and they are essentially used to design chips. That is, design chips means we either design ASICs, we design FPGAs. Okay. So what is the full form of ASIC? It is an application specific integrated circuit. Okay. And what is the full form of FPGAs? It is a field programmable gate array. Okay. So all these are variants of various kind of design platforms that we have. Okay. And the first step of the digital design flow is when you have a design in your mind and you would like to express it in the form of a language. Okay. And that for that particular thing we will, for example, today take the example of how to express designs using Verilog, understand some of its syntactical features, and also try to learn basically what is the philosophy of writing Verilog programs. Okay. So before I start formally, again I would like to add one more thing, that essentially now what you are doing is that you are trying to describe a hardware through a software, right? So in common language it is called that you have to think of a hardware, but you have to write a software. Okay. But the bottom line is that you have to think of a hardware, right? So we are not software engineers right now. Okay. So we are hardware engineers. So therefore whenever we have got a design in our mind, we have to be clear about the various design features. We have to be clear about the architecture of the design. Okay. So Verilog or all these CAD tools are not a way to bypass what we learn in our hardware classes. Okay. So we are first and foremost, we are hardware engineers, and then we learn how to use CAD tools or computer aided design techniques to make our jobs easier. Okay. But it doesn't reduce our task of essentially thinking of what is the hardware. Okay. So therefore you have to think of a hardware. Okay. And there was some person who was asked that, okay, what is the best CAD tool that you use? Okay. And he was actually probably he was the designer of the Pentium pipeline stages. Okay. So he gave a nice answer that the best CAD tool that I use is even now the paper and the pencil. Okay, so therefore your design has to be perfect. So you have to know how to design properly, and then only you know, and then only you rather go into the step of writing a Verilog or whatever. Okay, so therefore the first step, although I say is the Verilog language, or I mean writing HDLs, but actually the first step is your paper and pencil, where you sit down and think of your design specification and you draw a proper architecture and you start. That's actually the 0th step, you can say. Okay, so that's the first step. So what is the inherent, so I will rather, although I know that maybe many of us may not be knowing what is a Verilog language, but the question is, where is Verilog different from normal languages like C? Okay, so the thing which I will highlight is this feature of concurrency. So what is concurrency? So concurrency is an important feature that I require to express any piece of hardware. Why? Because you think of a normal breadboard design. All of us have done breadboard designs in our labs, right? So in our breadboard design, what we have is that we have got essentially a piece of design, and we have got various blocks which are functioning in concurrency, right? That is, they are working in parallel. So as opposed to that, in the language C, for example, what we have seen is a sequential way of executing, right? That is, we see that, okay, the first thing comes, the first line is executed, then the second line, kind of like that, right? So in Verilog or any other HDL, there is a power to model the concurrency, which is very natural to a piece of hardware. Okay, so you require constructs which would be able to express concurrency, right? So therefore, there may be two pieces of hardware which are even independent of each other. They may be dependent on each other, but you have to have a mechanism of expressing parallelism in your hardware, right? So Verilog gives you the following constructs to support concurrency, and they are as follows. They are always blocks. So there is assign statements, there are module instantiations, and there are non-blocking assignments inside a sequential block. So I will slowly, one by one, I will try to express this these steps, but let's go step by step. But before I start, this is a small note that I make, is that whatever I try, your simulating machine is essentially a sequential machine, right? That is, I am running a Verilog language, although it may have, I require concurrency, I understand that, but the machine on which I run my program is essentially a sequential machine, right? So no matter how many processors I do have, today I have dual core, I may have 4 cores, I may have 8 cores, right? But then I can write one more process than the number of processors which I also would require to run concurrently, right? So which means that although I require concurrency, but the processes or the processes has to be scheduled properly. Okay, so there is a scheduling involved. Okay, so that means that although I get a feel of concurrency, actually it is one by one of the steps happening and followed by the other. So it's actually a sequential thing which is taking place, but it gives you a feel of concurrency, right? So essentially your time does not have one axis, but there are two axes in the time. Okay, so therefore we will see how do we do that. So what is the problem? The problem is race. So that means you understand that if there are two blocks and I do not tell you properly that which block comes first, then you have the problem of race, because you can have race in your design. That means you do not know which block is going ahead. Okay, so therefore your simulation time and the real hardware that you have in your mind can have a mismatch. Okay, so therefore you have to be careful. So here is a small, suggestion, that is, if you think of a clean piece of hardware, that is, if you properly think of a good hardware, here comes your paper and pencil stage. If you have done your paper and pencil, that is the 0th stage properly, then you will find that the race and other things, other issues will be minimized. Okay, so that means that if you have thought of a proper design ahead, okay, then using this power of Verilog or VHDL or any other hardware description language, you will see that the chances of having a race conditions are reduced. Okay, so that's the way how I overcome race. So that in order to overcome race, try to think of a clean hardware and you won't have a race. Okay, so therefore here comes the importance of the 0th step. So here I start formally the 4th step rather, and this state is about how do I express Verilog. So rather than going step by step through all the syntactical features of Verilog, I would rather start using the Verilog. Okay, so I will start with a very simple example of a multiplexer, and we will see that slowly we are learning what is the power of Verilog, what are the syntaxes and what are the other features of Verilog. Okay, so here we see that in order to all of us know what is the basic circuit of a multiplexer, right? So in a basic circuit of multiplexer, you know that there are two AND gates and there is one OR gate, okay, and you have got an inverter which is essentially used to select either this AND gate or this AND gate, right? So therefore this is a simple hardware of a multiplexer. So I would like to express this particular piece of hardware using the language Verilog. Now you note one thing, that in the language Verilog you will find always that there is a modular description of the codes. Okay, so you have got something which is called module and there is something which is called end module. So this is the basic encapsulation of Verilog. So that means in a typical design what you would have is essentially a top diagram, that is you would have a top level architecture in your mind. Now this top level architecture will have smaller subparts, that is, say for example you can call this as module A and you will have say module B, okay, and all these modules will again have subparts. So therefore this description is also called modular description, and it's actually very important because when you design you do not make a flat design, okay, because your design has to be modular. So the reason is that very simple, that if I would like to replace a particular block, then I just need to go into that block and replace it by probably a better module. Okay, so that means that makes my design much more structural. Okay, so Verilog gives you the power of that. The power is by using this construct called module end module. So that means there are several modules that exist in your directory, and you design all the modules separately. Okay. So the first thing that you observe again is that you have got a module and the name of this particular file is, for example, or this design is, for example, mux. Okay. So therefore you have got a module say mux, and you see that you have got, so therefore what you are trying to design is a block which is called a mux, that is a multiplexer, and this multiplexer, the first thing is the interfaces, right? So therefore this block if you observe has got some interfaces. The interfaces are as follows: you have the port A, you have the port B, you have another port which is the select line, and the output is denoted by F. Okay, so these points or these interfaces through which your design or your module interacts with the external world are technically known as ports. Okay, so if you see that, so therefore in your Verilog also you have got this power of depicting these ports. Okay, so how do you declare these ports? What you do is that you essentially start with a bracket, a parenthesis, and inside that parenthesis you write all your ports one by one. Okay, so your ports are F, A, B, and select. Now some of your ports will be output ports and some of your ports will be input ports. Okay, so therefore you have to declare them as inputs and outputs, right? So you write output F because your F is your output port, and A, B, and select are input ports. Okay, so therefore if you see your language, what in the code you have declared them as inputs. So input A, B, and select. Okay, and inside this scope of your module and end module, the remaining part is the description of your circuit. Okay, so here what we have used is some constructs which are called AND gates and OR gates and NOT gates, because you have got AND gates in your design, you have got OR gates in your design, and you have got NOT gates in your design. Okay, so therefore the next question is that how do I write them? So you see that all these gates has got independent names. Okay, for example, if you see that this AND gate and this AND gate, although both of them are AND gates, have been given two different names. So therefore this is called AND gate G1 and this is called AND gate G2. Okay, and this is your OR gate, and this OR gate is named as G3. Similarly, you also have a NOT gate and its name is G4. Okay, so all these names, different names which are being provided to these gates, are called instances, okay, and therefore these are called instantiation of gates, okay. So therefore these names, that is this AND gates, OR gates and NOT gates, are also known as primitives, that is they are inherent primitives which are there, which exist there when you in your Verilog library, okay. So let's use them and see how do I connect these AND gates, okay. So for example, if you see that this AND gate G1 and this AND gate G2 is connected to your OR gate G3, okay, and how do I connect it? One of the input ports of G3 is connected to the output port of G1. Similarly, the other one, that is the other input of G3, is connected to the output of G2, okay, and the way how it is connected is by using a wire. So this wire, that is, if you see that this wire which exists over here is it also has a different name, and the name of it is denoted by F1, okay. Similarly, this particular wire is also named by F2. So you see that the way it is being connected is as follows. The nomenclature is as follows, the definition is as follows, that is the first entry in your list is the output of the AND gate, okay. So therefore this is the output and these are the two inputs of the AND gate, okay. The first we have the output followed by the inputs, okay. So you see that the input of G3, that is this particular OR gate, is being connected by the wire named F1, okay, and that is the same, and the same wire name is used to denote the one of the outputs of the AND gate, okay, the output of one of the AND gates, that is also F1. Similarly, the other output is also F2, and that is being used to denote the second input of the OR gate, okay, and that is the way how these AND gates are connected to your OR gates, okay. Similarly, you can follow the connection of your NOT gates also, and you can observe that one of the AND gates input, for example, the G1's input is N select, and that is precisely the output of your NOT gate, okay. So I think the rest of the things you can follow. So this is the mechanism in which it is connected, okay. So now these AND gates, okay, although they are essentially, I referred to them in the first code, but they are called primitives, okay. But this particular AND gate, if you write a piece of code of this nature, then you will find that they are not synthesizable. That means that they are not expressed in the library. So in order to express these AND gates, or rather if you would really like to write a code of this nature, then you have to describe these AND gates and OR gates separately, okay. That means that you have to write separate modules for these AND gates, and inside that you have to describe what an AND gate does, what an OR gate does, what a NOT gate does, okay. So that you have to write, means you have to write separate files, okay, and the suggestion is that all of these files, that is whenever I write a file, for example for this, I write a separate file and I call that top.v, okay, and similarly I write for this module A, I write, say for example, module A.v. So I write separate files, okay. So all of us, when you go to your laboratory, for example, for doing experiments, then essentially we will be using a Linux operating system, okay, or a Solaris operating system. So therefore you have to write separate files, and in all of these separate files you have to write an extension of .v, okay, and then you use the Verilog compiler to simulate your design, right. You compile your codes, that is you check whether there are any syntactical errors, okay, and then you check whether the output that you obtain is the desirable output or not, okay. So therefore the suggestion is that you, whenever you have got a module, you write a separate file for your module. Don't write all the modules in a single file, okay. That is also supported, but that makes your design look very clumsy, right. So therefore you write separate files, like you write top.v, and that is used to describe the module top, okay, and similarly for the other modules as well. So you observe that the other things that we have out here, for example, we have got a description called wire, okay, and you will find that the identifiers that are not explicitly defined are default to be wires. Actually they are default to be 1-bit wires. Now what are wires and what are regs? I will come to this very shortly. Yeah.
So in the previous examples, the ordering of shaping is important.
Yeah, exactly. Because that particular referencing, that is the referencing that has been done out here, like F1, A and N select, this ordering is pre-known, okay, it is known ahead. So therefore this ordering is extremely important.
So ordering
ordering of these statements. Okay, no, exactly not, because, well, yes and no, because the reason is that all these things are supposed to describe concurrency, okay, but really speaking I do not know, as I told you that we are running this over a sequential machine, right. So therefore, although we have got concurrency, but it is not actually concurrent. That means there is a small time interval after which one particular block is executed ahead of the other, okay. So that means it may happen that this OR gate comes into play first, okay. So therefore you have to be careful. So therefore you have to know how to describe all these AND gates and OR gates, okay. So in one sense you have got a scope of concurrency, but on the other hand you may also have some amount of race conditions involved. So you have to be careful how to implement them, okay. And so we will see them as we go ahead, okay. So we have got different kinds of assignments which we use to tackle these kind of issues, okay. So right now you can imagine that all of them are concurrent. Let's believe that all of them are concurrent, that is all of them are being executed simultaneously, okay. That is in the same timestamp. Okay, so we come to another way of coding this, as I told you that, so therefore this particular coding style, when you use AND gates and OR gates and NOT gates, are known as structural codes, okay. The other fashion in which I can code my design is using behavioral constructs. So what are behavioral constructs? Is constructs which describe your behavior, okay, and all of us know various behavioral languages. For example, the C was essentially, it has got a lot of behavioral features, right. You use if statements, else statements, so they are essentially behavior, because you know the logic, you know how your design should behave, right. So for multiplexer, for example, it's a very simple code, you know how it behaves, right. So how does it behave? You know that if this select line is 1, then B is selected, but if your select line is 0, then A is selected, right. And that is the way how you code this, and this particular coding style is a behavioral coding fashion, okay. So you see that the rest of the things are more or less the same as the previous code, but there is a difference here, and also we see a new construct which is the always construct, okay. And if you remember, I just briefly hinted that always is one of the techniques which Verilog uses to support concurrency, okay. So you see that always, whenever you have got multiple always blocks in a code, then all of them should be acting simultaneously, okay. And there is something like at, and inside there is a parenthesis. So inside that, whatever you write, this is actually technically known as the trigger list, okay. So or a sensitivity list, as it is written out here. So it is called a sensitivity list or a trigger list, and it contains signals whose change triggers the execution of this block. That means that whenever A changes, B changes, or select changes, then this particular blocks comes into play, okay. That means that, for example, these right hand sides are evaluated, the right hand side of the assignments are evaluated, and they are being assigned to the left hand side, okay. But what happens if A, B and select does not change? Then this block is not coming into play. So that means this variable f is holding the previous value, right. So it behaves like a register, okay, and therefore the data type of this f, okay, is also called commonly as reg f. So you write reg and you follow that by f. So reg is not a hardware register, as I will describe in much more details later on, but rather this reg is a data type, okay. It's just a data type. For example, in C we have data types like int, float, double, right. Similarly in Verilog, one of the data types is reg reg, okay. So reg is used whenever inside an always block or an initial block, as we will see, we have got variables which hold values, okay. That means it is holding a previous assignment, for example, then the declaration or then the data type of f is as reg reg, okay. But reg is not a hardware register, that is very important. So a reg behaves like a memory, it holds its value until it is imperatively assigned otherwise, okay. And the other important thing is that the body of an always block, if you see, has got traditional imperative code. So it's a very traditional code, right. This piece of code you have already seen in the language C, for example, okay. So it's a very commonly known piece of code, because that means it's a sequential code. Therefore in an always block, whatever you see are being executed one by one. That is, the first line is being executed first, next line. So you know this particular coding style, right. So therefore this is a traditional piece of code. The other way you can actually describe a multiplexer is by a continuous assignment. Okay, so the previous way was not continuous, because as I told you that whenever A changes, B changes, or select changes, only then the assignment takes place. Okay, the other way of writing Verilog languages is by using continuous assignments. So continuous assignments means these values like select, B and A will continuously assign some values onto this variable f. Okay, so therefore the data type of f is no more reg, it is not reg. Okay, because reg holds a value, it is not continuously being assigned. Okay, so rather in the, I mean, although I have not explicitly written, because it is implicitly defined, the data type of f is known commonly as wire. Okay, so if I had written wire f, it would have been perfect. Okay, so although I have not explicitly defined, the reason is that implicitly I have a 1-bit definition of wire. Okay, but if it is more than 1 bit, then I need to explicitly write here, describe here a wire. Okay, so if you know this particular technique, or rather this syntax, right, because this is very commonly used in C also, right. So if select is 1, then B comes into play, but if select is 0, then A comes into play. So A is being assigned to F. Okay, so in a continuous assignment, so I can rather depict it in this fashion, that all of these registers, for example in this case whatever values you have, okay, so you can have other values also, all of them are continuously giving some, or rather driving some values, and these values are being resolved by a resolver, for example. So there is a resolution out here, and that is being assigned to your wire. Okay, so that is the way how you describe a continuous assignment. Okay, right. So therefore if you observe that this particular resolution could be an AND logic, it could be an OR logic, or etc. Okay, so therefore although I have described something as wire, we have nomenclatures of this fashion. We have got W AND, we have got W OR and following. Okay, so if you see that the left hand side is always set to the value of the right hand side, that is any change in the right hand side causes a re-evaluation, but actually the difference between a continuous assignment and what we have seen previously, which is known as a procedural assignment, is that there is a continuous driving of the output. Okay, so the next thing that we come across is the identifiers in Verilog. So although I have written certain points here which you can see at your leisure time, but the thing is that if you use common names, then there is no problem. Yeah, the procedural assignment and a continuous assignment. Okay, so you have got a procedural assignment here. Okay, so this is the procedural assignment. So that means that whenever A changes, B changes, or select changes, then this value of f is being re-evaluated. Okay, that is, you do not re-evaluate at always. Okay, that is, it is not always being evaluated, but opposed to that, out here these values of select, B and A are continuously driving the value of f. Okay, it is not that only when select changes, B changes, or A changes, but all of them are continuously driving some values. Okay, another difference probably that we can say is that assign is used more for driving. Okay, so for example if you have got an idea of this kind in your mind, that is, you would like to describe, for example, a tri-state bus. Okay, that is, if you would like that, okay, there are some tri-state buffers. Okay, and depending upon the value of the select lines, okay, you would say that, okay, if it is A, if you give a particular value to A, then you get a signal here. Otherwise, if none of these assignments are on, that is, if none of the tri-state switches are on, then this particular bus is in the high impedance state. Okay, so these kind of designs, okay, for these kind of designs I would suggest to use assign statements. Okay. So the reason we can elaborate later on, but at this point of time let's just understand as a thumb rule. Okay, but the first difference is most important. So in Verilog you have got various logic values. So you have got 0 and 1 obviously because you are expressing digital logic, but the other thing that you express is cross and Z. So what is a cross and Z? cross is something which is undefined, okay, that is some wrong state, and Z is a high impedance state. Okay. So one example of cross could be as follows, that is, suppose there is a block module over here and there is another module, say module B, and both of them have been wrongly connected in the output. Okay. And you have got an instance when this block is trying to drive it high, whereas this block is trying to drive it low. Then what does the poor simulator understand about this point? It doesn't understand anything, right? So it will report you a cross here. Okay. So therefore cross and etc. are generally commonly are bugs. Okay, and that it may be a bug, it may be intentional, it may be unintentional, but when you have a cross in the output, then you should be careful, you should check it, right? And Z as normally defined, Z is a high impedance value. Okay, so these are the common logic values that you have, and the Verilog data types are as follows. We have got wire, we have got supply 1 and supply 0. Okay, the supply 1 and supply 0 are essentially nothing but the VDD line and the VSS lines. Okay, but they come very late in the design flow. They come when you are finally signing off your chip. That is, when you are finally done all your layout, back end, and everything is done. Then finally you add, if you observe your net list, you will find that in your net list there is something which is called a supply 1 and supply 0 in order to simulate. Okay, but apart from that, in normally what we will see in our lecture class, in our laboratory sessions, we will have data types. Which the most commonly known two data types that we will be using is wire, and the other one is REG reg. Okay. So as a wire is, as I told you, it's analogous to a wire in an ASIC, and it cannot store or hold any value, but it is continuously being assigned. Okay. There is another data type also that is commonly used. It is an integer data type, but this integer data type is used generally as an index variable. For example, for for loops, for while loops. Okay, but it doesn't have any hardware implication. Okay. And this is the description of the REG data type, that is a reg data type. So note that the register data type is comparable to a normal Verilog in a programming, compared to a normal variable in a programming language, that it holds a previous assignment. Okay. So the default initial value is X, and if you observe here, for example, there are two codes written out here. Okay. So you have got an REG example 1 and you have got an REG example 2. So if you observe here, we have got a construct which is called a posage of clock. Okay, so it is always at posage of clock. Q is being evaluated. Q is being assigned the value of D. Okay, so if you observe this, you would easily understand that it is the description of a D flip flop. Okay, because whenever there is a positive edge in the clock, then Q is being assigned the value of D. D is the input. Okay, so out here the data type of Q is reg. Okay, because whenever there is a positive edge of the clock, then only Q is being assigned a value. Rest of the time Q is holding its previous assignment, right? So whenever this data type holds a value, then the data type is reg. Whenever a variable holds a value, the data type is reg. Okay, similarly, but there is a note out here, written out here, that it says that a reg is not always equivalent to a hardware register or a flip flop or a latch. Okay, so a reg is not necessarily a hardware flop or a hardware register or a hardware latch. Okay, so if you see that example 2, you would find that this is a purely combinational design, because it says that whenever A or B changes, then C is being assigned the value of A or B. So what would be the hardware for this particular block? The hardware for this particular block would be very simply like this, that is, you have got A and you have got B and you have got an OR gate, and you connect and you obtain C. Okay, so therefore C is not a register or a flop or a latch. Okay, so that means although my data type is an REG reg out here, but it doesn't imply that reg would lead to a flop or a register or a latch. Okay, so it is just a data type, and it has got nothing to do with the actual hardware that you obtain. Okay, so this is actually a cautionary note. So as I was trying to point out that there is a difference between driving and assigning. Okay, so for example, programming languages, if you use normal statements like always and things like that, then you would find that essentially they are nothing but techniques through which you assign variables. Okay, that is, you assign values. As opposed to that, there is sometimes in our hardware, that is what we would like in our hardware would be a scenario like this. Okay, that means in this particular scenario I am not really trying to assign a value, but I am trying to drive a value, and there is a slight difference between driving and assigning. Okay, that is, in a normal assignment statement there are various things that takes place one after the other, and the last assignment stays. Okay, but in a driving, all the signals which are driving, for example, like this particular input, all these three inputs are driving a value here, right? So it may happen that this is trying to drive a z, this is trying to drive a 1, and this may be trying to drive a 0. Okay, but depending upon my resolution, as I told you in this previous case, that is, depending upon my resolution, the logic of this particular bus would be determined, right? So I may have a wire AND logic, I may have a wire OR logic, and kind of things like that, right? So that means in this particular scenario, I would suggest you to use the assign technique of coding, whereas if you have a multiplexer in your mind, where multiplexer means that depending upon your select value, some of the signals are being assigned. So either you choose this, or you choose this, or you choose this. So in this particular scenario, you use the always mechanism. Okay. So use the construct of always, and in this particular scenario, when you are describing a bus, you rather use a assign construct. Okay. So this point I have already told you that reg is not necessarily a hardware register, it can be a simple combinational design as well. Okay. So I am not really going into this. So this is the example that I was talking about just now. That is, if you write a code like this, that is always at A or B or select, you write like this. Then if you synthesize, this will be inferred as a multiplexer. Okay, but if you want drivers, that is, if you want to describe a design of this nature, that is, if you want to describe a bus in which you are driving various values, then what would be the code? Then the ideal code would be like this. Okay. So if you see the code out here is that you have the difference is that you have been using more assign statements and not always blocks. Okay, so if you see that out here, all these blocks will be essentially working in concurrency. That is, this block, this line, and this line, all of them are essentially running concurrently. Okay, it's not like that one comes after one after the other. Okay, so you have got the philosophy is that in this case Z is being determined by the logic of A, B, and C all at the same time. Okay, it's not that Z comes first, A comes later on. I mean, this line comes first, this comes next in the sequence, this comes third, and this comes fourth. Okay, there is no sequential evaluation. Okay, it's just concurrently done. Okay, so you have got a scope of concurrency. So the summary is that if you would like to describe a multiplexer, then go for a code of this nature. But if you would like to describe a driver, then you go for a code of this nature. Okay. The next thing is to describe a number. So therefore, as I told you that I can have a 1-bit bus, you can have more than 1-bit buses also, right? So for example, that if you have a design, say an adder for example, and in your adder you have got for example two 4-bit numbers which you would like to add. Okay, so you would like to add A, and you would like to have B, and you would like to produce a sum which is also of 4 plus 4 will be 5 bits for example. Okay, and then you also have a carry. Okay, so carry is how many bits? 1 bit, right? Just 1 bit is exported as a carry, and you have got a 5-bit sum. Okay. No, if you have a 4-bit numbers, two 4-bit numbers. Now I would like to produce keep a 5th bit. Okay, yes, you can keep 4 bits, and then you have got 1 bit. Okay. So how do you describe this? How do you describe a particular port, for example? Okay. So in this case, this port, like input A, the way it is written out here is input 3:0, and then you write A. Okay, and you write B. Okay, and the output is denoted as output 3:0 S, and the other output is C. So C is If you write in this fashion, it is implicitly means 1 bit. Okay, it implicitly means 1 bit. So that is the way how it is being declared. So if you see the slide, for example, what it is written is that first you have to write the width, and then you have to follow by the corresponding radix value. Okay, so therefore, if I would like to assign a value to A, for example, then I would write like this. I would write assign A equal to 4 tick B1, for example. Okay, so if you observe that this is the width, this is the radix, and this is the value. Okay, so Verilog will not keep any track of sign, but if you would really like to take care of the sign, like if you would like to have a floating point signed operation, then your architecture has to take care of that. Okay, so this is the way how you define numbers. Okay, you write numbers in Verilog. So first you have got the width followed by the radix. This radix could be h also. H means hexadecimal, and then that is followed by the value. So in a hexadecimal you could have like A, B, things like that, right? So okay, so that completes how you write your or describe your numbers. And then you have got the hierarchy. I have already told you what is there in the hierarchy. So if you come to the first thing which I started with, you have got, this is your hierarchy, right? So you have got not one level of your design, but you have got several levels of your design. You have got a top level followed by various levels, and that is followed by sub levels. So all of them are being described by modules. Okay, so you have got separate modules through which you do that. Okay, so therefore these modules are essentially instances. So therefore the way how you, again you have to instantiate these modules at a level, and you have to write that module A, module B, and you have to connect them by wires. Okay, and the connection would be similar to what you would have done in your first example, where you would have where you have defined various ands and ors, and you have connected them by wires. Okay, so similarly at your top level also you will have your module A, module B, and more modules maybe, and you have to connect them by wires. So it's similar to that what you do in a breadboard design. Okay, and for that, I mean, in order to do the connections, you use the idea of wires. Okay, so that is quite simple, and you can also see my slides. There are various references you can see, like you have got MM1 for example, which is one module, and there is another module MM2. Okay, so therefore this particular declaration or definition you have already seen, right? We have defined like and then this is the way how I have defined in the first example. Okay, so this is called connect by position. So note that here I think one of you also told that this ordering is very important, right? I need exactly to know what is the meaning of Y1, what is the meaning of A1, and what is the meaning of B1. Okay, the order is important, but in this case when I am connecting by name, you see that I have written as dot A A2, dot B B2, and dot Y C2. Okay, so in this case it is called connect by name. So in this case the ordering is not really important, because what it means is that in my block my mod or MM2, that is the name of the instance, these ports are named as A, B, and Y. Okay, but in my top level of my design, this wire A is being the nomenclature of this, or this is being named by the wire A2, this is being named by the wire B2, and this is being named as by the wire Y2. Okay, so if I would like to connect another block to this in my top level, then this Y2 is being used to connect. So this is the wire at the top level. Okay, but this Y is the name of the port. So that means that is internal to the design. But the advantage of this kind of definition is that I am not really interested in knowing that which comes first and which comes later on, right? I could have changed this dot A A2 and dot B B2, and still it would have worked fine. The ordering is no more important. Okay, but only I have to write some extra terms. I have to know exactly the name of the ports, and I have to write them. Okay, but here I have, so if for example if somebody designs this for me, this MM2, and says that this is my input ports, then ports names is A and B and Y, I am not really interested about what goes on inside. Okay, I just can use these names as my interfaces. Okay, so this is probably more suggested to use. So this was probably a better way of instantiating. Okay, so next we come to something which is called sequential blocks. So sequential blocks are some group of statements, and these group of statements are inside a begin and end scope, and you know what sequential means. As the name suggests, it goes one by one, that one step is followed by the next step. Okay. So a sequential block is sometimes an always block, for example, and they are executed repeatedly, but whatever is there inside a sequential block comes into play one after the other. That is, the first line comes, then the next line comes, next the third line comes, and so on. Okay. So similarly, you have got something as you have got an always statement that we have seen. You have also got an initial statement. So initial statement, the only difference between an initial statement and always statement is that the initial statement comes into action only once. That is at the first, when you start your simulation. Okay, and only at that time. Okay. So then we come into something. I think I've already told you that when you write assignments using always blocks or initial blocks, then that particular technique is known as procedural assignments. Okay, and the other way is called continuous assignments. And this is an example. This is a slide which shows you all kind of assignments in one place. It says you that there are procedural assignments and there are also continuous assignments. And for example, if you would like to express your holiday, that is, if you would like to express your weekend, you can write as follows. You could have written that assign that weekend is either Saturday or Sunday. Okay, so this is an example of a continuous assignment. I hope you understand this, because it means that whenever Saturday and Sunday, these variables are continuously driving the value of the weekend. Okay, but if I would have liked to write this as a procedural assignment, then how would I have written that? Using always blocks, right? And this is an example how you write. So you say always at Saturday or Sunday, your weekend is equal to Saturday or Sunday. Okay, so this is an example of a procedural assignment. The difference is that in this case, the data type of this weekend has to be made as reg, because when the Saturday or Sunday does not change, then this weekend variable is supposed to hold the previous value. Okay, so the data type of this is reg. So this is an example of how you can mix up assignments, and you can basically whatever you can express using procedural assignments, you can express using continuous assignments as well. Okay. So I would like to conclude rather with one very important assignment technique. I think the rest of the things you should be able to follow on yourself, because there are so many things to talk about this particular thing, but this is a rather involved issue, so I will rather talk about this. You have got two kind of assignments. One is called blocking assignments and the other one is called non-blocking assignments. Okay, so a blocking assignment looks like this. Okay, blocking assignment looks like this, and a non-blocking assignment looks like this. Okay, so what is the difference between this assignment and this assignment? So as the name suggests, a blocking assignment or a blocking procedural assignment must hold, it stops the execution of the subsequent assignment. That is, if you find two blocking assignments, then until and unless the first blocking assignment gets over, the next blocking assignment does not start. Okay, that's why it's blocking. Okay, but as opposed to that, you have got non-blocking procedural assignments, which is being denoted by this particular symbol of less than equal to. So in this case, it doesn't block. It actually supports concurrency. That is, all the blocks are taking place simultaneously. Okay, so for example, let us take this case. We have got A equal to 1, B equal to A, and C equal to B. So this is an example of a blocking assignment, right? So what would be the final result? First, A will be assigned as 1, next B will be assigned as A, but then already A has become 1, right? So B becomes equal to 1 also. And what about this C? C also becomes equal to 1, B, but B has become equal to 1, right? So therefore finally A, B and C all are becoming equal to 1. Okay, but if I would have written this as like this, that is A non-blocking 1, B non-blocking A, and C non-blocking B, then all of them, if they are taking place concurrently, then that means that A will be equal to 1, no doubt, but B will become equal to the old value of A. That is, before this updation, whatever was the value of A, right? And if the C, variable C, would also be updated by the old value of B. Okay, so if you would like to think of a hardware for this, because finally whatever we are writing is for hardwares, and if you think of the hardware for this, then what would be the can you guess, for example, what will be the hardware for this and what will be for this? Yeah. Can you tell me? Can you categorize as combination and sequential, for example? So there is an old value of A means there is a notion of time, right. So therefore this essentially would be better to describe your sequential logic, okay, and this would be better to describe your combinational logic, okay. So therefore the hardware looks like this. You see that you have got just buffers A, B, C connected with one driving, and in this case you have got a sequential shift register, okay. So there can be more interesting examples also. See, for example, consider this code. This remains the same as this, and inside your begin and end you write okay. So can you draw the diagram that is the corresponding hardware for these two codes? So you see that the only difference between these two codes is that this particular block has been changed from blocking to non-blocking, okay. So if you think of the hardware, what will be the inherent difference between these two? So this we have already seen, right? This is nothing but, I mean this we have rather seen. So this would be like nothing but a shift register, okay. That is, you have got two flops, okay, and this output is being denoted as Y2, and this is being used to drive. So this is nothing but Y1, and this is your input, okay. So in this case also you would have two flops, and this is clear that this Y2 becomes equal to this Y1. If this is Y1, this becomes equal to the input, right? And what about this point? Where should I connect? I should connect it to the input, right? So if I connect this to the input, then this is the way how I connect, right? So you see that you have got two parallel flops, but here you have got two sequential flip-flops, okay. So you see that there is a slight difference between how you realize your hardware, okay. So therefore this, whether you should be careful whether what you want. If you want the normal shift register, then you go for non-blocking assignments, okay. But if you want this kind of hardware, then you use blocking assignments, okay. So you have to be careful about what you want. And as I told you that actually there are more involved issues about, if you go into more details, that is how the processor or how the scheduler inside your normal sequential computer schedules various operations. That is, all these assignments, you know that there is nothing concurrent, right? So there is a mechanism in which one takes place followed by the other, right? So there is actually a way or ordering of the scheduling, okay. So there is, first all the right hand sides are evaluated of the non-blocking assignments, followed by all the blocking assignment evaluations, and that is again followed by all the non-blocking assignments, okay. But they are more involved and detailed issues. So since for the lack of time I would like to skip all those things, but rather let's concentrate on the basics of blocking and non-blocking assignments. Here is a very simple example, and I think you would be able to follow and understand properly. That is, for example, whenever there is an example of a blocking assignment, so which means that whenever A1 and B1 changes, okay, so it's suppose it changes at time t, okay, and then when does this assignment takes place? It takes place at time t plus 3, right? But this particular assignment will block the execution of this. So that means this Y1 will be assigned a value at time t plus 4, right? So that is precisely what you have done. But what about this? The first will take place at time t plus 3, so there is no difference. But what about the last one? T plus 1, right? So that is the difference, okay. So therefore in this case it is using old values, right? So I hope it is clear, right? So there is an order dependency of the concurrent segments, but these are more involved issues, and I think I am running out of time, so I would skip these issues. So I would come to how are simulators used. Okay, so therefore the first thing that you have done right now, or rather seen some glances into, is that you have got a system model, a description, which you have described using a piece of Verilog constructs. Okay, so now this particular model is supposed to be a very something which I call as a synthesizable piece of Verilog code. Okay, that means all the constructs which you write, all the language features that you use, essentially have got hardware connotation. Okay, for example, always can be synthesized, but initial block is not synthesizable. Why? Now, because your initial block takes place only once. Okay, but in your hardware you do not have that idea. That is, you do not have something which is called initial, right? Because, for example, see, I mean, there is one inherent difference from C and Verilog. So suppose I would like to have a piece of code like this, like sum equal to sum plus I. So let us consider the C scenario, like the scenario in case of C. Okay, so that means that whenever I comes in, I am adding into the variable sum. Okay, so all of us know that if I would have to have a code of this nature, then I have to initialize my sum to 0, right? So that is what takes place in a normal C code, right? So therefore I can say that, okay, for I equal to, say, I equal to 0 to say 10 and I plus plus. Okay, I can have a scenario like this, right? So in this case, sum has to be initialized like 0. But if I would like to do the same thing on a hardware, then what I require is as follows. The first thing that I require to do is I require to draw a block diagram and try to understand what are the interfaces. So what is the interface here? There is something which is called the input line, right? And there is something which is called the output line. So there is this port which I called, for example, input, and then we have got this output. So therefore there is a point when I start the computation. After that, when whatever comes in the input is getting on added and stored in a register and finally being exported, right? But here that means that internally there is a register which I called, for example, sum, but somebody has to initialize this value of sum to 0, right? But normally in a language C, I can do that very easily because I can write sum equal to 0 and go ahead, right? But here when you declare something as reg, for example, reg sum, then you cannot write like assign sum equal to 0 and then go ahead. Okay, but rather on a piece of hardware, if you have to make something 0, then you have the notion of reset. Okay, so that means you require an extra input out here, and I call that, say, RST, and you have to explicitly write a code which makes the sum 0 when there is a positive edge maybe of the reset. Okay, so if you have to draw a proper amount of hardware, you have to think of more details, you have to think of more internals of the hardware. Okay, so for example, you have got a clock. For example, I can give you an example, like whenever there is a positive edge of the clock, the input comes in and gets added. Okay, but first of all, when there is a reset, at the positive edge of the reset, the sum register gets loaded with the value of 0. Okay, so if I would like to write a piece of code for this, I can do it as follows. I could have written as always at pos edge of clock or pos edge of reset. I write a begin and an end. Okay, and inside that I write like if RST, that is if there is a reset, then this sum is being given a value of 0, else sum plus I. Okay, I guess the rest of the things you can fill up, so I am not filling up all those things. So there is a name also here. So all these things you have to fill up, and there is an end module over here. But inside this, the reason why I give you this example is that you have to be careful about this notion of reset. Okay, there is nothing that you can first of all declare as 0 and then go ahead, because if you think of a piece of hardware, and if you have, for example, a wire inside a hardware, you don't have that idea, right, that somebody will connect it now to, say, for example, 0, that is the ground line, and then change that connection inside the chip and again connect it to somewhere else, right? So there is no idea as such. So therefore, if you think of a hardware, explicitly you have to have mechanisms or architectural features through which you can do those operations, right? So for example, so in this particular example, we have used the reset for doing that. Okay, I know that there is a flip-flop and there is a port which is called a reset. A reset can be a synchronous reset, it could be an asynchronous reset also. So in this example, I have used can you tell me whether it is a synchronous reset or an asynchronous reset? There is an asynchronous reset. Okay, so whenever this, so it says that always at positive of clock or positive of reset. Okay, that means that whenever the reset comes, whenever there is a positive edge of the reset, these always block will come into play. Okay, but if I would have removed this positive of reset, then it becomes a synchronous reset. Okay, so that is what I mean by synthesizable. So you have to use proper synthesizable mechanisms through which you describe your system model, and then in order to test your design, you have to write something which I called as a test bench, and it's actually non-trivial to write a good test bench because 70% of design industry works on writing test benches only. Okay, so design effort, design money goes into writing test bench, but the test bench is used to give stimulus to your design and also obtain responses and finally check your result. Okay, but the reason why I have separated these two portions is because for describing the system model, I have to use synthesizable components, which means that I have to have all constructs which can be mapped into the library that I have. Okay, and the test bench, whereas for the test bench I can use more high level constructs. Okay, so although I have not defined or rather told you that actually in Verilog there are some other high level features also which are more suited for writing test benches. Okay. For example, I use there are scopes of using fork join statements. There are tasks. There are these initial blocks which are used to give the initial loading. Okay, but all of them are non-synthesizable, which means that they do not have a hardware connotation. Okay, so that means for these things cannot be used to describe a system model. So if I would like to describe a system model, then I have to use synthesizable component. That means my codes should not be using these kind of features. Okay, that is the system model should not use this kind of features. So I would so let us see one example of this my old multiplexer that we have. So how do I write a test bench for a multiplexer? So you see that if you would like to test your multiplexer, first you have to write a module, again test marks and etc. You have to instantiate your multiplexer. That means you have to write my marks, for example, and this is, so therefore this is what? This is referencing by position or name? By name. Okay. So and then you start giving signals, giving input, giving stimuli to your design, and you see that you have got an initial construct in which you have given s equal to 0, a equal to 0. So all these are nothing but inputs. So you are giving your inputs gradually one by one. You give one, and this hash 10 means after 10 simulation times, and again after 10 simulation time you give a different output, and then the corresponding output you can observe by using something which I call a dollar monitor. Okay, so there is something which is called a dollar display as well. So you can use a dollar monitor or a dollar display, and using that you can. So this syntax is quite similar to that of a printf statement in C, and you can observe the output. Okay, so although this is a mechanism in which you observe, but the other very commonly used technique is by observing waveforms. Okay, so in your lab you will find there are tools which gives you the explicit waveforms also. Okay, so waveforms are actually more helpful for debugging purposes. Okay, so so this is an example of a card speed controller, and maybe I don't know whether I have time, but this is an example how you actually this is a complete example of a little bit complicated example. So you see that there is an FSM that I have drawn here. FSM means a finite state machine, and this finite state machine has got, for example, 4 states. You have a card which is initially a stop state, goes to a slow state, and then goes to a medium state. It goes to a fast state. Okay, and it can also change states in between depending upon whether you are accelerating or braking. Okay. So you can describe this kind of hardware. If you would like to describe the controller of this card, you can describe. But the reason why you can also see these slides are available to you. But actually in this case, I have combined all my mechanisms of coding. That is, I have combined the data path and the control path. This is not a prudent thing to do. Ideally speaking, you should actually separate all of. I mean, whenever you design a complicated circuit, I think you will have complicated examples of designing processors and things like that. You should always try to separate your control path and your data path. Okay, so this style is followed in the coding of complicated designs like arithmetic logic units and etc. So we will not having time. So therefore, if you would like to describe, this is the way how it's done. So you see that this is my data path and this is my control path. All of them are being separately designed. but I really know that you would not be able to appreciate this so fast. You have to go through the code slowly, but for that we require time, and the slides are available, you can see them and we can discuss later on. So I would like to conclude. So therefore finally the idea is that write codes which can be translated into hardware. So the summary is that these initial blocks and delays, that is this hash 10, hash 4 or etc. are not synthesizable, that is they cannot be translated into hardware. So in short, you should be writing codes with a hardware in mind, that is the final thing. I have seen codes after 4 or 5 years of working, people have written codes which look like a C language. It doesn't give you any advantage of using power of Verilog or things like that. So first you should think of a hardware, that the 0th step is very important. You should think of a good hardware, and then only you should write a Verilog code or anything. Okay, you should go into the design flow at all. So therefore, in other words, do not depend too much upon the tool to decide upon the resultant hardware. And finally, remember that you are a better designer than the tool. Okay, so the tool is used to assist you, and not blindly rely upon your. It's not a magic potent that I want a design, I will just define it and it will give me a design. No, I am the designer. I have to think of the design first, and then only I can describe a piece of design using whatever language. Today we have Verilog, tomorrow we will have some other language, but the main thing is to think of the design. So we should, whenever we are doing VLSI, for example, the first thing that, when we are doing digital VLSI, for example, being more specific, we should be thinking of the hardware very clearly. We should be thinking of the architecture very clearly. If we do not have a proper architecture in our mind, then we have got nothing to contribute. Okay, we cannot contribute to the performance. We cannot make our designs better. That is the bottom line. Okay, so another suggestion is that if you would like to learn a language, there is only one way you can learn a language, is by writing codes and running them in the lab. Okay, so therefore, please use your lab sessions properly, write codes, and then only you will be able to learn whether this language or any other thing. Okay. Thank you. So if you have any questions, you can ask me. So these slides are available on my website. Okay, but I think you will be getting from the